In chapter 15, we talked about intensity, and we based intensity on based on a sphere. Remember that intensity is equal to the power divided by, for a sphere, it's 4 pi r squared. And because we have r squared in the denominator, that means that intensity is related to 1 over r squared. And this means that intensity is not linear. Now, this relationship was found by Alexander Graham Bell for his study of the telephone. And he came up with a unit that he called the bell. And it was a relationship based on sound. Now, the one question that needs to be asked when we talk about intensity and decibels or bells is in relation to what? And this just means that the bell, or we use a decibel, it's just going to be a tenth of a bell, is going to express some kind of ratio. And that ratio needs some kind of standard or a basis to measure. Now, bells are quite a large unit, and we tend to use decibels. And the formula that we use is some value beta, and the units are, well, decibels really don't have a unit, but we put dB just so that we understand that we are talking about decibels. And that's equal to 10 times the log base 10 of the intensity divided by our base intensity, or I naught. Now, I naught is equal to 1.0 times 10 to the minus 12 watts per meter squared. And this is considered the threshold of human hearing. And so we have our ratio of I over I naught. Now, why do we use the log function? Well, remember, our intensity is not linear, but the log function will make this, makes the intensity ratio linear. That's the main reason why we use this decibel formula. Now, remember that decibels are unitless. As I mentioned, we put decibels there just so that we know that we're talking about this ratio. Now, another interesting thing that we can do is, let's say I'm standing from a speaker over here, and I have some power signal going into the speaker, and if I don't move, then I'm going to have some intensity because of that power and the surface area. And if I increase my power, but I'm staying at the same spot, it's going to be related to the intensity. I haven't moved, but the power has changed. So we can use that to redefine decibels to relate it to power. So if I have beta, and we'll do dB is equal to 10 log, and let's express intensity in terms of power. Power over 4 pi r squared, we'll call it power 1, over some base power, and I haven't moved, so it's 4 pi r squared, same r squared, and if I simplify, I get 10 times the log of P1 over P naught. So now I've related decibels to a power ratio with the caveat that I'm not moving. Assume no location change. Now I can have this power P naught equal to different things. So if I make P naught equal to 1 milliwatt, which is 1 times 10 to the minus 3 watts, we get a definition, and we call it decibel milliwatt, or dBm, and that's going to be equal to 10 times the log of P1 over 1 times 10 to the minus 3 watts. And you'll find this a lot in engineering, especially electrical. Electrical engineers love to do this. Because it gives them a way of relating power in a quick, easy way. Another option is if I set P naught to a microwatt, so our beta value, we're going to have decibel microwatt is equal to 10 log power over 1 times 10 to the minus 6th watts. So these are some important decibel relationships that you can use. You can relate it to sound here, because we're dealing with intensity, or you can relate this to sound. You can relate this to electromagnetic power? Radio waves, basically. Gain in an amplifier. A lot of different ways when you start relating power. There's a lot of different topics that you can use this concept for. So it's important that you know both of these possible uses or multiple uses for decibels. Now in the next video we're going to discuss some other important decibel relationships, and one of them is going to be important for you to remember because it will be used quite a bit.